What happens when language models start learning from themselves, synthetic users stop behaving like controlled experiments, and diffusion models reveal a hidden leave one out structure? In this episode, we explore three striking papers that challenge how we think about AI training, evaluation, and generation. From model collapse as a form of cultural evolution, to the hidden bias in simulated user studies, to new ways of improving diffusion-based language models. These results reveal that small design choices can dramatically change what our systems learn and how we trust their outputs. Let's explore the first paper, Model Collapse as Cultural Evolution. This paper argues that model collapse in LLM self-training is not just a statistical failure mode, but an instance of cultural evolution under iterated learning, and it tests that claim by repeatedly fine-tuning LLMA 27B and Mistral 7B for 10 generations on 50,000 passage datasets in English, German, and Turkish. The key novelty is a discriminative prediction. Compositionality should first rise and then fall if compression operates without communicative grounding. That prediction is confirmed with strong effect sizes, including hedges G equals 1.87 and BF10 equals 247 for the non-monotonic compositionality trajectory, and it persists even from a maximally regular PCFG seed, ruling out a noise removal explanation. Task-grounded quality filtering using an external evaluator on extractive QA, NLI, and summarization is the only intervention that sustains compositionality. Random 70% filtering behaves like no filtering. The paper also shows frequency-dependent regularization matching the human curve from Morgan and Levy, 2016, with R2 equals 0.94 monotonic morphological regularization across English, German, and Turkish, and distributional narrowing with zip f exponent alpha falling from 1.07 to 0.82 inches, Llama, 2 and 1.07 to 0.86 inches, Mistral. A dimension-specific loss order emerges as well. Pragmatic constructions disappear before morphological ones, which disappear before core syntactic constructions, with entrenchment frequency correlating with survival generation at R equals 0.73. Overall, the study reframes model collapse as a compression-communication trade-off and suggests that self-training pipelines need task-grounded verification, not random subsampling, to preserve linguistic structure. Let's explore the second paper. The illusion of intervention. Your LLM simulated experiment is an observational study. This paper shows that LLM-based synthetic user experiments often do not implement randomized trials. They behave like observational studies with intervention-dependent selection bias. The authors formalize user drift as a causal confounding problem. When a persona L is held fixed, the latent user state XL can still shift differently under treatment A equals 0 versus A equals 1, so the observed effect tau, OBS, estimates a mixture of treatment effect and selection bias rather than the average treatment effect. They diagnose drift with negative control outcomes, Z attributes that should be invariant to the intervention, and quantify distributional shift with total variation distance between PZ, A equals 1, L and PZ, A is gelijk aan 0, L, across 6 models, including Quen 330B, A3B, GPT, OSS, 20B, Gemma 4, 31B, IT, Gemma 3, 4B, IT, and Gemini 3 Flash. They find substantial baseline TVD in Opinion QA, Book Opinions, and Movie Lens, with the smallest Gemma 3 4B showing especially large drift. They then mitigate bias by iteratively eliciting additional confounders, LL, especially task-relevant variables such as political ideology, media habits, or book-movie selection behavior. This adjustment often reduces TVD and stabilizes effect estimates, but generic demographics can initially worsen bias before targeted confounders bring it down. The key novelty is methodological. The paper argues that persona prompting plus intervention is not enough for causal identification, and that internal validity in LLM simulations requires negative controls and confounder adjustment, not just better mimicry of human responses. Let's explore the third paper, Uniform Diffusion Models Revisited, Leave One-Out Denoiser and Absorbing State Reformulation. This paper shows that in uniform diffusion models, UDM, the standard plug-in bridge parameterization is not optimized by the usual denoising posterior, but by a leave one out posterior that predicts token from all noisy tokens except XT. The authors derive exact conversions among the denoiser, the leave one out predictor, and the concrete score, and use them to train a UDM leave one out model directly with standard cross entropy on Open Web Text, OWT, and 1 billion word, LM1B. This consistently improves validation, perplexity, and the generation frontier, with top-P sampling at matched entropy, reducing GenPPL from 54.8 to 42.2 on a representative OWT run. They also show that applying top-P or temperature after converting a denoiser into leave, one-out form, is better than applying sampling heuristics to the denoiser itself, and they build an informed Gibbs predictor corrector sampler without any auxiliary network, which Pareto dominates ancestral sampling at the same runtime. Separately, the paper reframes UDM as an absorbing state process with a random latent absorbing token U, yielding absorbing state UDM, AUDM, and a resampled variant, re-AUDM, that preserve the UDM joint law while recovering mass diffusion-like carryover and remasking operations. On language modeling, AUDM adds only 7 M parameters, about 4.1% overhead, and improves likelihood over UDM and all zero-shot baselines. On Sudoku, leave one out UDM reaches nearly perfect solve rate, while AUDM and re-AUDM match or exceed mass diffusion, supporting the claim that the UDM-MDM gap is driven more by parameterization and sampling design than by the corruption marginals themselves. That's a wrap on today's AI paper highlights. Thanks for watching.